Hello and welcome to MD3. In this recording or recordings, we will be looking at Fourier expansions. Now, this material is covered in a different way, but it is covered in Riley, Hobson and Ben's chapter 12, except we'll be approaching this in almost a reverse manner. Okay, so let's start. Now, the requirements for this particular recording is that you have watched my recordings on Hermitian operators and function spaces. We'll be using some of the properties of these operators here. So let's start. Consider the operator L hat, which is given by minus d squared by dx squared in the interval 0 to 2 pi with periodic boundary conditions that y naught is equal to y of 2 pi and y prime of 0 is equal to y prime of 2 pi. Alright, now what I'd like you to do, and this is an exercise, show that with these boundary conditions, this operator is self-adjoint, so L is equal to L dagger, and L is also Hermitian. And if you remember the definition of Hermitian operator, it means that not only is L equal to L dagger, but that those boundary terms vanish. And this is kind of worked off for the most part in Riley, Hobson and Ben's 17.2. So have a look there, which is here. And you can see the problem worked out here. It's they've defined L is equal to d squared by dt squared, and so this is nearly the same problem. You should be able to show it. Now, if L is Hermitian, which it is, then we know that the following must be true. 1. The eigenvalues of the operator L must be real. That says real. That's pretty bad handwriting. Okay. The Eigen Functions of L will be orthonormal. And the third is that the Eigen Functions of L form a complete set. Now, we did not prove that it forms a complete set because the proof of this is somewhat involved, but I did tell you where you could find it. Alright, so what it means then is if we set up the eigenvalue equation, so L hat operates on phi n of x is equal to lambda n phi n of x, we can solve this. Now what I've done in solving this is not use lambda n, but I put a lambda squared there, and the reason will become clear soon. So L hat operates on phi to give us lambda squared times phi. This leads to the differential equation. L hat is of course minus d squared by dx squared, so this is the differential equation we need to solve. And we haven't learned how to solve second order equations yet, but these kinds of equations with constant coefficients, the coefficient of the derivative term is just minus 1 and the coefficient of the function term is lambda squared, that's another constant. These can be solved by using the ansatz or the guess. Phi is equal to a times e to the alpha x, and if you substitute this guess for phi in here, what you end up with is an equation for alpha, and you get alpha is equal to plus minus I times lambda. Okay, this means that phi is of the form a e to the plus minus I lambda x, and what we will do is we will fix a by just normalizing phi in the interval from 0 to 2 pi. The other thing we're going to do next is that these boundary conditions, those periodic boundary conditions, are going to select particular values of lambda. So not all phi will be allowed, but only those for which lambda satisfies certain conditions, which allow phi to satisfy the boundary conditions. Alright, so we start with the boundary conditions then. We've been told that phi of 0, or I had put it up there as y of 0, but it doesn't matter, this is the function, phi of 0 is equal to phi of 2 pi. You put in this expression for phi, and what you end up with is that 1 is equal to e to the plus minus I lambda times 2 pi. And this is satisfied for lambda integer, positive or negative integer. And therefore, the phi n's are eigenfunctions of the operator L hat are given by a times e to the plus I n x. And I've chosen just the plus sign here instead of the plus and minus because I've allowed these integers to take both signs, plus and minus, which covers both cases. Alright, so I covers all integers, positive and negative, including 0, and the eigen functions are now given by these exponentials. And the eigenvalues will be lambda squared. Lambda is equal to n. And this is why I chose the eigenvalue to be lambda squared up there. It's so that we wouldn't have a square root appearing in here, but it wasn't essential. We could have just as well used lambda as the eigenvalue. So we normalize these eigenfunctions as before. Phi hat of n is defined as phi n of x divided by the norm of phi n. The norm of phi n is the square root of the inner product of phi n with itself. And if I now choose, and this is a choice, I'm going to define my inner product to be the one with weight function wx is equal to 1. So there's no weight function. In fact, every point is weighted equally. Then the inner product of phi n with itself is given by the integral from 0 to 2 pi. Those are the limits of integration of this particular space of the periodic function. And then we have a star e to the minus I nx times a e to the plus I nx dx. Now, by the way, whenever you have a complex function and you're taking the inner product like this, you do need to complex conjugate the function that appears in the bra side. So we did need to complex conjugate this exponential and the coefficient here. And if you work it through, what you end up with is that the norm of phi n is the modulus of a times root 2 pi. And that leads to the normalized phi n is 1 over the square root of 2 pi e to the in, where n is an integer. And just to check, we have another boundary condition that the derivative is also periodic. So phi prime at 0 is equal to phi prime at 2 pi, and I'd like you to check to see that this function satisfies that condition too. Okay, so now we have our eigen functions, and we know that these eigen functions are special. So first of all, are they orthonormal? In other words, is the inner product of phi n with phi m equal to delta mn? And this is a simple proof. I'd like you to just try it out on your own, but it's also given here. Let's have a look at how this goes. So the inner product of phi n with phi m is given by the integral 0 to 2 pi phi n star phi m. Now once again, and let's remind ourselves, the weight function by choice has been set to 1. Now once you make a choice like this, you've got to keep it consistently the case. So you do have to then remember that the weight function is set to 1 in every other inner product. You can't change it once you have defined it. Alright, so this is simply the 1 over 2 pi, the integral from 0 to 2 pi of e to the minus I nx e to the plus I mx dx. And that can be simplified to the integral 1 over 2 pi, the integral 0 to 2 pi of e to the I m minus n of x dx. And I'd like you to show that this is equal to 1 if m is equal to n. I think that's pretty easy to see. If m is equal to n, then this exponential is just 1. So the integral of 1 from 0 to 2 pi is 2 pi divided by 2 pi. That gives you a 1. And then it's equal to 0 if m is not equal to n. So please show this. And that's simply a statement that this is the Kronecker delta. So this is delta mn, which is exactly as we required. So this set of functions is indeed orthonormal. Okay, so that verifies that particular property. Now what this means then, by the way, in case you're wondering why I'm not writing stuff down, it's because there's so much of mathematics in this particular recording that if I wrote things down, it would be a rather extraordinarily long recording. So I am not writing things down, which I know it's, well, that's what I'm going to do here. I'm not writing things down in live, let's put it that way. Alright, so now let's take a function f of x, which is defined in the same interval, so it's periodic with the same in the same interval. So f of 0 is equal to f of 2 pi, and its derivative is also periodic in this interval. Then what we know is that f of x can be written as a linear combination of those eigenfunctions, because those eigenfunctions are eigenfunctions of a Hermitian operator in this interval with these boundary conditions. In other words, that infinite set of phi n eigenfunctions is a complete set in this particular space. So f of x then is written as the sum n goes from minus infinity to infinity. It's a discrete sum from minus infinity to infinity of Cn, some coefficients, times the phi n of x. Now how do you find those coefficients? We find them the same way we found the coefficients of a finite vector. Take the inner product with one of the basis functions. I've taken phi m here. So whenever you take the inner product, don't choose the index which you have used here. I've used n as a dummy index here. It's summed over all n. Don't choose an n, choose something else. So it's phi m, the inner product of phi m with f. That's the inner product of phi m with this entire sum. Now if the sum is convergent, then we can move the sum outside of this inner product, and then we have the sum n goes from minus infinity to infinity of Cn. Remember, the Cn's are scalars, but they are in the ket side, so they can be brought out without any complex conjugation. And then this phi m inner product with phi n goes inside the sum, and this of course is just delta mn as we have seen, so we get a single constant Cm. In other words, any function which is periodic in 0 to 2 pi can be written as the sum n goes from minus infinity to infinity of the inner product of phi n with f, so that's a scalar, times phi n of x, and that's a function. And this is known as the complex Fourier expansion. So this is the Fourier expansion of a function f of x using this complex basis functions. Why complex? Because these phi n's are 1 over the square root of 2 pi e to the I n x. Okay, so let's see how this works then. Take an example of a square wave. Now I've chosen a square wave so that it has period 0 to 2 pi, so the period is 2 pi, and it's 0 for in the range 0 to pi, and then it's 1 from pi to 2 pi. Okay, I've called it square in quotations here because the height is 1 and the width is pi, so that hardly looks square, but that's what we tend to call these things. Okay, so we know what our basis functions are as before, and I put a note here. Whenever you're doing a Fourier expansion, always check to make sure that the basis is appropriate. And we'll see how to, this particular basis is periodic in 0 to 2 pi. So you might ask, what happens if my function is periodic in minus 1 to 1 or something like that? Well, there are ways to modify this basis systematically, and we'll see how that's done. But in this particular case, this basis is in fact appropriate for the range 0 to 2 pi, so we can use it. And we write down our function f of x written in terms of this basis phi n with these are the coefficients. So the coefficients are the inner product of phi n with f, which means if you want the Fourier expansion of f, we need to work out what these inner products are. The inner product of phi n with f is given by the integral 0 to 2 pi of phi n star of x times f of x dx. Once again, this weight function has been set to 1, and by now you should know why this is the case. If you have forgotten, then scroll up and you will find out. Alright, so this is the integral from pi to 2 pi. Remember, this f of x is 0 from 0 to pi, so the only non-zero contribution is from pi to 2 pi. When f of x is 1, that's why it doesn't appear here. and it's the integral of 1 over the square root of 2 pi e to the minus I n x. Don't forget to complex conjugate the basis function because it's in the bra side, and dx. Now if n is 0, then what you will get is pi over the square root of 2 pi, and if n is if n is not 0, and this is something you'll have to show, what you end up with is I times 1 minus 1 to the power of n divided by n times the square root of 2 pi. Please show this. These kinds of integrals appear quite often when you're doing a Fourier expansion, and more often than not, you've got some function of x in there, and you've got to use integration by parts repeatedly. So you need to get used to these kinds of integrals and get them down quickly and reliably. So that's what this integral is. So we know our expansion coefficients, and therefore we can write down f of x. This is the n equal to 0 term, which is pi over n naught, plus all the terms for which n is not equal to 0. So n goes from minus infinity to infinity, but it's not equal to 0. And these are the coefficients here, times phi n of x. If you now put in what the phi naught and phi n are, you get an expansion which is a half, plus the sum, n is not 0. These are the coefficients, and e to the I n x. And this is the Fourier expansion of this particular function. So in a way you could stop here. Yeah. So this is the you could stop over here. But you could also realize that this is a real function. So let's have a look at it again. It's either 0 or 1. I mean, it's a real function. And what we have done is we've represented this real function in terms of complex exponentials. And there's also an I over here. Now what that should tell you is that there must be a way of combining these exponentials and this I such that the result is manifestly real. Now we know this, if the left hand side is real, the right hand side has to be real, but it's not manifest at the moment. But there is a way of doing that, of making the fact that it's real manifest. We keep the half as before out there, it's already real. And then we write down the sum over here. The sum, remember, it goes from minus infinity to infinity, excluding the term n is equal to 0 on the top. And then if you put any n even over here, then minus 1 to the power of n, if n is even, gives you a plus 1. So the numerator is 0, which means n is odd. All even terms go to 0. Alright, so that means now what I've done is I've taken the term n is equal to 1 and written it up here. N is minus 1, written it down here. So that's n is equal to plus minus 1. N is plus 3 is up here. N is minus 3 is down here. And you can go on grouping these terms like this. As I've said, even n terms don't contribute. Now what you can see there is that if you add these two terms up, and I'm going to leave this for you to show, you get something which is proportional to the sine of x. If you add these two terms up, you will get something proportional to the sine of 3x, and this goes on. And in general, and this is, you need to complete this proof, f of x is equal to a half minus the sum over odd n only, 2 over pi n times the sine of nx. And in fact, I have plotted a few of these first 7 terms, the sum of the first 7 terms over here, and you can see very clearly that indeed we are getting an expansion which is oscillatory about 0 up to pi. Here's 0, oscillatory about 0 up to pi. Then it switches continuously, it has to be continuous, to oscillate about 1 up to 2 pi, and this repeats. I'd like you to notice a couple of things. First of all, the oscillations are about 0 and 1, 0 and 1, but it's never equal to, I mean, it never really settles down. You have to have an infinite number of terms, and even then, if you read an advanced book on Fourier series, you'll find that there will be wiggles at the edges, and there will be wiggles there because you've got a discontinuity. If you look at what's happening here, at 0, for example, if I draw a line up here, this function takes on the value of 0.5 at x is equal to 0. Likewise, at x is equal to pi, it takes on the value of 0.5. While the function we wanted to represent with this Fourier expansion, it was discontinuous. It would be 0 and then abruptly go up to 1 and then abruptly come down to 0. But the Fourier expansion, truncated at any finite value, and in fact even at infinite value, will go up smoothly. It's never a perfect representation of a function with a discontinuity, but it's almost there. All right. So that's the part about how we develop Fourier series. Now, we have a few questions. The first question is, what happens if you wanted to change the period from 0 to pi to something else? For example, x naught to x naught plus L. Yeah, so we don't have to start at 0, and we don't have to end at 2 pi. We can end at x naught plus L. So the period here is L. What happens if you have real functions? Now, we have seen above that if you have real functions, then you can combine these complex basis functions to give you, in the case above, only a sine term and not a cosine term. I'm going to comment on this before we move on. And then finally, what happens if you have general functions that are not periodic, but they are defined in a finite interval? Can you represent those by a Fourier series? And it turns out that you can, and we will see an example of this too. Now, before we move on, I want to just comment on why in the above expansion did we end up with just a sine term and a constant term? What happens to the cosine term? Now, if you have seen a Fourier series before, you would have known that you expand in terms of a sine and a cosine. And the answer has to come down to symmetry. Here's my Fourier expansion. This is the function I want to represent with a Fourier expansion. Now, if you look at it carefully, you will find that if I superimposed a sine wave on this, let me use one of these colors. I'm going to take a sine wave that's moved up by half. So so here's a sine wave. So that's a horrible sine wave. And if I move that up by half, then it comes up here. I'm probably drawing this pretty badly. Yeah, I'm drawing this pretty badly. So we don't want sine of 1. I'm going to stop this video here because I'm pretty sure I'm messing something up at this point. Okay, figured it out. What I should have noticed here was that I have a negative sign in front of my expansion in terms of the signs. So I ought not to be drawing sine of x. I need to be drawing minus sine of x. So let's use another color for this. If I draw minus sine of x, then this will go down the other way. And I hope you can see this horrible green. That's sine of x. Now if I draw cosine, and I'm going to use a hopefully better color. If I draw a cosine, now the cosine is symmetrical about the origin. So the cosine looks like this. If I move it up by 1, it will be, that should go through here. This is really bad, so let me redraw this cosine. It's going to be 1 if we are at the origin, and it's going to be minus 1 over here. Yeah, so this is what a badly drawn cosine looks like. But basically, it just has a wrong phase. it's not in phase with the square wave. That's probably all I wanted to say. And because it's not in phase with the square wave, in fact it's out of phase by exactly pi over 2, we don't have any cosines in this expansion. And that's why the expansion is entirely in terms of the sine. Okay, now I'm going to end this particular part of the video here, of the recording here, and we'll come back to answering these questions in the second half of this recording.